All right, well, hello again and welcome to online lecture 2. The topic of this lecture will be probability. So let's dive right in and start talking about this. So we start off with the mathematical fortune teller who says, "You will win the Lotto Max jackpot, yay!" With probability 0.0000349, assuming you purchase a ticket. Okay, so mathematical fortune teller, a little different than your average fortune teller. So what is probability? Essentially, it's the likelihood that an outcome of interest will occur. Okay, so what's an outcome? It could be the result of an experiment or observation. It could be a coin toss, heads or tails, a dice roll, or a card from a deck. So how do we determine probability? How do we figure it out? So we start off by determining the number of possible successful outcomes or outcomes of interest. Okay, so let's say you're playing a coin game with a friend and you bet heads and they bet tails. Then your outcome of interest for you would be heads. You want it to come up heads. So that's one. To determine the number of all possible outcomes, well, coin only has two sides, heads and tails. So that's two. Divide the number of possible successful outcomes by the number of all possible outcomes. So that's 1 over 2, or 1/2, or 0.5. That would be our probability. Okay, so let's talk through an example here. You have a jar that contains 100 jelly beans. 9 of the jelly beans are green. So what would be the probability of picking a green jelly bean? Feel free to pause this, take a moment, think about it. Okay, so the answer would be 9 possible successful outcomes over 100 possible outcomes, right? There were 9 jelly beans that were green. There were 100 total jelly beans. So 9 over 100, or 0.09. That's the idea behind probability. So now, after we just talked about our very first formula, which was probability, right? Number of possible successful outcomes over total number of possible outcomes. We are going to discuss our first symbol. And there are a lot of symbols in this class, so it's really helpful to get to know them. On an exam, you won't want to try to figure out what the symbol is in addition to figuring out the problem. You kind of want to know those. So anyhow, our first symbol is P, lowercase p, kind of italicized, and that's a symbol for probability. Now, probability is typically written as a decimal, kind of like we just have been doing all along, right? We said 0.5 for the half. We said 0.09 for 9 over 100, whereas chance is written as a percent. So the probability of outcome A occurring, we would say, is Z over 100. Like with the jelly bean, the probability of getting a green jelly bean was 9 over 100, or 0.09. Whereas the chance of outcome A is Z%, or 9%. So this kind of begs a interesting question here, which is, how do we go from probability to chance and from chance to probability? Okay, so let's talk about that for a moment. The way you go from probability to chance is just multiplying by 100. So we took the 0.09, we multiplied by 100 to get 9%. So if we do multiplication to get from probability to chance, what must we do to get from chance to probability? We have to go backwards. We have to think of what's the opposite of multiplication. Typically, the inverse of it would be division, right? So now we're going to take our 9%, divide by 100, and get 0.09. Okay, so given that, let's go through a couple more examples. what's the probability of getting a heads on a two-sided fair coin? Well, this is one we already talked about. And the probability of getting a heads is 0.5, right? 0.5 or half. Chance of getting a heads, what's the chance of getting heads versus tails, is 50%, right? 50% of the time we'll expect, doesn't have to work out this way. That's the thing about probability. It's all about chance. It's all about maybe what will happen, right? So chances are 50% of the time we'll get a heads. Okay, and the probability of 7 of diamonds, think about that one for a moment. How would we even figure that out? Okay, so what we have to figure out first is that we have 52 cards in a deck, standard deck, right? We're not going to include the jokers or anything. So if there are 52 cards in a standard deck, 7 of diamonds is only one of those cards, so it would be 1 over 52. And if you actually divided that out, you would have your answer. Okay. And for chance 7 of diamonds, just take that number and multiply by 100, and you would get your chance for 7 of diamonds. Okay. So let's talk about the range of probabilities. A probability cannot be less than 0 or greater than 1. That's its full range. Okay, so something with a probability of 0 has 0% or no chance of happening. Something with a probability of 1 has a 100% chance of happening. Now, we tend to live between these two. We very rarely talk about probability of 0 or probability of 1 in statistics. But let me just throw out a fun example for you guys. Let's say you have a not so great friend. They're okay, they're an acquaintance. They call you up, 2 in the morning, and they say, hey, I'm moving out tomorrow starting at 6 a.m. And yeah, I'm moving across town, and my building has no elevator, and the building I'm moving to has no elevator, and so it's a 4-story walk up both ways, and I do have a ton of books, and if you help me out, I do have a rotten banana that I can give you as a reward. You might say there's a 0% chance of that happening. Okay. Now, on the other hand, if a really, really good friend of yours calls you up at a reasonable time and says, hey, listen, I have to move a bunch of pillows, and I'm just moving 2 stories down from the 4th floor to the 2nd floor. And yeah, there's elevators. And by the way, I have this extra Xbox One I'd be happy to give you if you help me out. If you're an Xbox fan, or if you're feeling that they're a really good friend, then you might say there's a probability of 1 or 100% chance that you'll help them out. Okay, so that's kind of a jokey way of talking about it, but really in statistics, we are living between 0 and 1, between 0% and 100%. Okay. So this is just a kind of a funny thing. I like to think outside the P=0 box, says Lincoln. And Honest Abe just develops a sense of humor, much to the chagrin of prob stat students, right? Because it's landing on its side, and it's not supposed to do that. We always talk about, 50% chance of heads, 50% chance of tails, and here it is landing on its side. I did learn some number of years ago that the fattest coin, which is the nickel in the US, there is not a 0 probability of its landing on its side. It's very, 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 very small, but it's not 0. So there's a fun fact for you. Okay, so let's move on from here. And what I want to do now is talk to you a little bit more. Now that you have a sense for probability, I want to talk to you a little bit more about some coin flips and really talk through some probabilities associated with coin flips. So what we're going to do is talk through this with using a scenario. And the scenario is going to be that you have a friend that you like to go to lunch with every day. And you decide to play this game with your friend that if your friend if the coin comes up heads that you flip every day, your friend gets a free lunch you buy. If the coin comes up tails, you win and your friend buys lunch. Okay, so that's how we're going to play. So let's look at how this might work out. Okay, so let's say the first day you play comes up heads. Okay, 50-50 chance of that happening. You're not too worried. Now you've played for 2 days, and that's what this shows you right here. So we want to figure out the probability of all the different things that could happen when you play for 2 days. Okay, so for example, let's start off by figuring out on the left side, let's look at the coin flip number, and let's look there and figure out what are all the possible things that can happen. Well, one possibility is that you could get 2 tails in a row. That's the first line there, tail and tail on day 1 and day 2. That would make you very happy. It meant you got 2 free lunches. Another thing that can happen is it could be heads on the first day, tails on the second day. Or it could be tails on the first day, heads on the second day. Now in those 2 cases, you each would have won 1 time, you each would have lost 1 time. So you would have kind of come out even. And finally, you could have had 2 heads on the first day, heads on the second day. So let's start on the right, now graphing that out. Well, let's start with number 1 head, okay? So that's in the middle there, and we see that that can happen 2 different times, and that has a probability of 0.5. It's 2 different ways that can happen out of the 4 possible outcomes. 0 heads happens only 1 way. 1 out of 4, or 0.25. And that's in that top scenario, 0 heads, where you had 2 tails. And 2 heads happens also only 1 out of 4 times, or 0.25, when you get 2 heads, as in the bottom row says head and head. Okay, so 50% of the time we'll probably, or 0.5 probability, will land with 1 head. 2 heads only happens 25% of the time. 0 heads only happens 25% of the time. Let's move on. Let's continue playing the game. Okay, now we've played the game on 4 different days. And let's see what's going on here now. So let's start with the most likely thing to happen. If you play on 4 days, you would expect that 2 heads, 2 tails, right? That's the most likely thing to occur. So how often does that happen? Well, we can see based on the graph on the right that it happens a little bit between like 35 and 40% of the time. That's how it'll work out. How about 1 head or 3 heads? Well, that'll happen around 25% of the time. How about 0 heads or 4 heads? That's getting kind of rare now. Let's say your friend had gotten 4 heads on every single day. You might be starting to wonder, because that only happens a little more than 5% of the time. So you might be feeling like your friend is pretty lucky if they got 4 heads on 4 consecutive days. All right. Now you've played the game 20 times. And it almost looks like, again, it looks like the most common thing to happen, 10 heads. 10 heads, 10 tails across 20 days. It almost looks like it's impossible for you to get 20 heads or 0 heads, but it's not impossible. It's just very, very, very unlikely. So before we try to understand the 20 heads or 0 heads, let's first look at 10, let's consider 10 tosses. Let's say you just played the game for 10 days. Well, if you noticed, what's going on is the possible number of outcomes is growing kind of exponentially. So when we get up to 10 tosses, we already have over 1,000 outcomes. It's 1,024 outcomes. So if you ask about, if your friend got 10 heads on 10 days, there's only about a 1 in 1,000 chance of that actually happening. Now I want you to think for a moment, now we've got 20 tosses. How many possible outcomes are there now? How many different ways can we record all the possible outcomes that can occur? And if you think about it for a moment, guess something in your head, I will tell you that it's a little over 1 million. Little over 1 million outcomes, okay, with 20 tosses. It's actually 1,048,576 outcomes. So getting 1 out of that million or so, if your friend won every single day for 20 days in a row, that would be about 1 in a little over 1 million, or point a lot of zeros, 95. Okay. So again, very, 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 very unlikely. I'd be checking the coin at that point, right? Okay. All right. So here's there's a couple reasons why I wanted to build you up. A, I wanted to get you a little more familiar, a little more comfortable with this notion of probability. B, I wanted you to see this shape that was starting to form. Does this look familiar to anyone? Maybe you've seen it somewhere before. It's starting to look like what we call a bell-shaped curve or a normal curve. Now, we're not going to talk a lot more about that today, but it will come back around. And I'm going to come back to this concept that it's very, very interesting that even when we're dealing with something like flipping coins, that we can wind up when we look at the probabilities of something like a bell-shaped curve. But for now, I just want you to notice it. Okay. So since we're talking about probability, let's talk about a game that's based on probability. And the game is one that most people know, but I'll explain it to you in case you don't. It's called rock, paper, scissors. And what we want to know about rock, paper, scissors is the game fair? Okay, so how does it work? You have 2 players, and what you do is you have 3 symbols. A rock, which is a closed fist. Okay, paper, which is a flat palm, and scissors, which is the number 2 horizontally. Okay. Each player hits the other hand twice, and on the 3rd time gives the symbol that they wish. I'm trying to throw a rock here. Okay. And who wins? Well, rock beats scissors, paper beats rock, scissors beats paper. And so we might ask ourselves the question, is the game fair? And what do we really mean by that? What do we mean is the game fair? Okay. So let's consider that. What makes a game fair? So if you are thinking it has something to do with having an equal chance of winning or losing, then you're absolutely on the right track there. Yeah, that's what we're talking about in this context of fairness. Okay. So we can address this question using the power of probability. So all we have to do is figure out all the possible outcomes that can happen. So it's possible that player A will throw a rock, as you can see written in red, paper, or scissors. It's also possible that player B will choose rock, paper, or scissors. And so if you look at the combination of each one, you will see what happened. So in the top left corner, you see rock, rock, or RR, right? Because they both threw a rock. Going across the top, you will then see rock, paper, and then rock, scissors. This is all what's happening if player A threw rock and player B threw rock, paper, or scissors. Then you can look at the second row and you can see you have paper, rock, paper, 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 scissors. And in the third row, scissors, rock, scissors, paper, scissors, scissors. So we might ask ourselves to start off, okay, these are all our possible outcomes, right, in this table right here. How many are there? How many different outcomes can happen? 9, right? That's what I see. I see 9 different possible outcomes here, right? What we just talked through, 3 rows of 3. So what's the probability of any single outcome? It's 1 over 9. It's 1 over 9, or 0.111111. Okay. So now what we're going to do is we're going to label each outcome as either player A wins, player B wins, or draw. If player A wins, we'll shade the cell red. If player B wins, we'll shade the cell blue. And we'll use yellow for a draw. Okay, so we can see that this actually works if we look at a couple of the cells. You notice down the diagonal are all yellow because they're all draws, rock, rock, paper, paper, scissors, scissors. We notice here we have paper and rock combined in red, PR, because paper covers rock. And beneath that we have SR, or scissors and rock, or rock crushes scissors, so it's labeled blue. So what's the probability that player A wins? So remember, to figure out a probability, we have to count up the number of successful outcomes over the total number of outcomes. So the number of reds over the total. So looking at this, I would say it's 3 over 9, or 1/3, or 0.33. How about player B? There we're looking for the blue ones. I also see 3 here, 3 over 9, 1/3, 0.3333. And how about a draw? Yep, I see 3 yellow, 3 over 9, 1/3, 0.3333, repeating. Okay, so now I ask you the question again. Is the game fair? I think it looks fair to me. You have an equal chance of winning and losing, and even drawing in this case. Okay. So some of you, if you are familiar with the show called Big Bang Theory, might know of the game Rock, Paper, Scissors, Lizard, Spock. Well, we're going to explore this game in class to kind of further our understanding of probability. I'll end by trying to show you this video right here that came from the show about rock, paper, scissors, lizard, Spock.
I'll tell you what, how about we go rock, paper, scissors?
Oh, I don't think so. Anecdotal evidence suggests that in a game of rock, paper, scissors, players familiar with each other will tie 75 to 80% of the time due to the limited number of outcomes. I suggest rock, paper, scissors, lizard, Spock.
What?
Oh, it's very simple. Scissors cuts paper, paper covers rock. Rock crushes lizard, lizard poisons Spock. Spock smashes scissors, scissors decapitates lizard, lizard eats paper, paper disproves Spock, Spock vaporizes rock, and as it always has, rock crushes scissors.
Okay, I think I got it.
Rock, paper, scissors, lizard, Spock.
Okay, so that's what we'll be looking at in class. So make sure you're there. It should be a fun one. Okay, that's all I have for you guys today. Be well, and I'll see you next time.